DC circuit analysis. Okay, when I call your name, go ahead and... Do we have any? Let's see, what do we have? Homework. Actually, let me look at your notebooks today when I call your name. We'll just come up here and let me see that you took notes. Corey? Okay, good. That's good. Benjamin. Here's your first quiz in digital. That's a digital class.
Yeah. I need to talk to you before the lunch break. I finally got my book for this.
What's the digital book?
Yeah, I got them both.
You weren't here during last class, is that right? Okay. Okay. I would get the notes from, well, they're actually online. You can go through the notes. And you can watch the videos on Moodle. I would go through and watch those.
With everything.
Okay. Okay. Dakota?
Notes.
Mm-hmm. From last class?
Yep.
Okay, thanks. Jesse?
I don't know which ones they are.
That's them right here. Yeah, that's it right there. Good job on drawing those. Nice. Christopher.
Starting from here.
Okay,
down.
good.
The notes from the slide the other day.
Okay, good. Okay. Frederick. Robert. You didn't take notes, okay. Gary? Okay, good. Don? That was good. Okay. Good job. Clarence.
Yep. There's another page in there.
Okay. Okay, good. I have found that there's a very strong correlation between people who do their homework and take notes and the A students. Those things seem to correlate very well together. So, I'm going to pass out an assignment.
Let me get one of these. My dad's in the hospital.
Oh, you have to go?
Yeah, my dad's in the hospital.
Oh, okay. Sorry about that.
I'm gonna have to go. Let me get one. This side sheet.
Yeah, this is the... So on here you can see that module 1.5, which is last class period, we talked about components, symbols, and the reading assignment for that section is going to be chapter 2 in your book, so you can do that over the weekend, over the holiday, yeah, of your, this book, the blue applied circuit analysis book, chapter 2, resistors. And then when we get back, then I'll give a reading assignment over parts of chapter 9 and 10, just actually the beginning part, so it's not the more difficult parts of those sections. It's just the beginning, introductory parts of those chapters. So And then I also said to work examples and the practice problems and put those in your lab notebook. Okay.
Where's that on here? The homework, chapter 2.
1.5.
Yeah.
Did everybody get?
Yeah.
Oh, you didn't.
Thank you, brother.
Yeah. The reading assignment is chapter 2 in this,
Yes.
and work all the examples and practice problems in this reading section part.
Okay. So in other words, when you're talking about this, you're talking about that book.
Yeah.
Okay.
ACA in this book it says ACA. Read ACA. ACA is applied circuit analysis.
Gotcha.
That's what the ACA means.
Gotcha.
All right. So today the topic is going to be capacitors, coils. Actually, let me start recording this. Today's topic will be capacitors, coils, and transformers. So capacitors, we've I think you guys have seen the capacitors in the back that we've had on the table, but there's many different types of capacitors. They all do the same thing, and that is they store electrons. When we had the lesson on static electricity, and we talked about being able to transfer electrons, we mentioned that we group electrons in a quantity called a coulomb, which is millions of electrons. Similar to the way that we talk about a dozen eggs, we group those things together. In the same way we talk about charge in a quantity, okay, of electrons. Now those electrons that we stored by rubbing the plastic tube with the piece of wool, the same type of charge can be on the plates of a capacitor, okay, on a piece of metal, and that is stored energy, and that can be stored on a capacitor in the form and display of voltage and a current property. So you can actually discharge and charge capacitors to have static charge be remained on the plates, or you can have that static charge discharged through the leads or load or whatever it might be. So the basic construction of a capacitor is simply two metal plates in parallel with each other. Now what do you think is going to happen if you have, these electrons on one plate, which we say has a negative charge? Okay. What do you think is going to happen to the plate on the bottom plate? Yeah. It's going to, what we do is going to induce a positive charge. The way it induces a positive charge, think about the plate on the bottom as originally being electrically neutral, right? Electrically neutral. So what's going to happen when you put the top plate? Let's say that we move the top plate from a long distance away, and we get it closer and closer until they're very close to each other. What's going to happen? Well, when we talked about induction, the electricity in the bottom plate is going to separate out. It's going to separate. Okay? The electrons on the top are going to actually repel the electrons in the plate. Okay? So all the electrons in the plate are going to be repelled to the bottom side of the plate. That's going to leave what we call positive charge on the top side of the plate. Right? Okay? Now if we ground this plate to ground, what's going to happen? Well, where's the bound charge and where's the free charge? The bound charge is the plus charge. They're bound. The electrons are free to move, and they're gonna move to ground. Why? Because that's what free charge does. It goes to ground. So what you're going to wind up with is you're going to wind up with negative charges on top with these all these electrons, and you're going to wind up with positive charges on the bottom plate. What is that going to represent? It's going to represent a voltage. Yeah, it's going to represent a voltage. Now, the farther apart you separate these plates, the less bound charges you're going to have, so the voltage is going to go down. The closer you get those plates together, the more bound charge you're going to have, and the higher the voltage is going to be. In fact, what you're going to find is that an equation Q equals C times V is going to be met. And that is the amount of charge on those plates is going to be equivalent to the capacitance, and the capacitance is equivalent to how close those are. And we'll talk about the capacitor equation later, times the voltage. So this is the fundamental capacitor equation, which you guys don't really have to memorize right now because we'll get into that later, but I wanted to briefly go over what that equation was. But really the only point that we're trying to get across right now is the basic construction of a capacitor. How is it made? It's made by having two parallel plates next to each other. One plate induces a voltage into the other plate, and the free charge is free to move off of one plate, and then you have the bound charge. So you always wind up with opposite charge on both sides of the plate. Always.
It says two conductive materials. Are two different conductive materials?
No, they're the same. They're normally the same.
Be two copper plates.
Two copper, aluminum, whatever. The important thing is actually the dielectric. The material in between the two plates is called the dielectric. Okay. Die means between, and electric means actually means insulator in the way that it was originally defined. It's an insulator that's in between the two plates. Electric. The term electric was coined to be whatever objects tended to have electric charge when you rub them. And so what happened was that insulators originally became termed as electric because when they would rub it with a wool sock or whatever, they would tend to attract things. As it turns out, they weren't really electric. They were not conductive. So that's the reason why they were coined electric, is by the fact that they were insulators. I don't know if that makes sense to you guys, but so the dielectric, the substance in between, actually what's found is that an air capacitor is a capacitor that has a dielectric of air. Okay? It's actually found that the capacitance will be greater if you put something other than air in between the plates. Something other than air. So the capacity or the capacitance or the amount of charge, it's all the same thing, tends to increase if you put something like paper, plastic, mica, glass, ceramic, air, well not air, but ceramic. Any of those other things other than air is going to make a better capacitor. Yeah.
Have the plates in a vacuum.
I would think it would be close to air, but I'm not sure. It'll probably be a little bit different than air. Yeah, depending on what's in the air. Because air is oxygen and nitrogen. 80% oxygen. Actually, it's 20%. Is it 20%?
As far as heat's concerned,
it's 20% oxygen, 80% nitrogen. But so it's going to be. It would change it a little bit if you had a vacuum. You have no oxygen or no nitrogen, so it would be different. So why does let's just think about this for a minute. Why do you think having paper in the middle would increase the capacitance.
Is it better insulated than air?
Let's say we have a top plate and we have a bottom plate. Let's say the top plate has free electrons all on it, okay, and we get it kind of close to this bottom plate. What's going to happen? Well, we learned Coulomb's law. Coulomb's law says that there's going to be a force on the electricity inside this bottom plate, and that force is proportional to what? How's it related to the distance between the plate?
Square of the distance.
Inverse of the distance
Inverse of
squared.
square.
Yeah. So what that means is that it's going to repel the electrons, which, since the atoms are bound, when the electrons move, it causes a effective positive charge on this plate. Okay, and of course, if you ground this side, then the free electrons are just going to go to ground. The minus free electrons. Well, how can we shorten? So the distance, if we make the distance smaller, then we're going to create more of a force, right?
Right.
Okay. Well, what if we don't reduce the distance, but instead we put something in here called the dielectric, and what the dielectric is going to serve as the intermediate thing to conduct that charge. For example, what's going to happen to this dielectric? I can't really erase all of this. It's going to have the same effect. This minus charge up here is going to repel any electrons in that piece of paper. Okay? And all the electrons are going to be on the bottom side of that piece of paper. The plus charge are going to come up here, right? So now the electrons are effectively closer to that bottom plate now. Effectively closer, right? Everyone agreed? They're effectively closer. And so you can actually take these two metal plates and squish them all the way against that piece of paper, and it will not allow electrons to flow through it, but it will induce charge across it. Charge conductor, but it conducts. It induces static electricity, but it does not induce current electricity. It inhibits current flow, but prohibits electrostatic induction. So that's how they work. So one of the best performing dielectrics actually is ceramic. Ceramic capacitors have what we call as the lowest equivalent series resistance. Now, some of the dielectrics you put in here actually. Let me erase these. It's too busy over here. Some of the dielectrics you put in inside here actually do conduct. Because normally these touch each other. These two plate, the top plate and the bottom plate. Let's just say that this is metal. This is some type of like ceramic or something. And sometimes you can even have like electrolytic capacitors. They have like a gel inside there. Like a gel or a liquid non-conductive, like for example an oil or something, would be non-conductive electricity, but it would induce a voltage really well, induce charge very well. But anyway, the dielectric you put in here can have a resistance from one plate to the other. Okay, but ceramic is one of the ones that has one of the highest resistances, so that's considered good to have a high resistance. We call this actually equivalent series resistance. The dielectric's resistance we call equivalent series resistance, ESR, equivalent series resistance. So ceramic capacitors are more expensive than other types, but they are the best. One of the best. Let's see here.
So you want something that will ionize the light.
Yeah. You want something that is going to pass static
Right.
electricity or induce a static electricity, but not pass current electricity. Yeah.
Used to run a dielectric press at CBG, making interior parts for Freightliner. And now I actually understand why it would shock the hell out of you if you got too close to it.
Oh, really?
Yeah, it's a static electricity.
Okay.
Yeah.
Huh. Okay, well, that's good.
What kind of press was it?
Dielectric press.
So how can you make a capacitor? You can actually make a capacitor. We did this in past classes. I used to have an introduction to electronics engineering technology where we did things like this, but you can make a capacitor from 2 sheets of aluminum foil and wax paper or paper,
Right.
Really the purpose of the wax paper would just be just to have something. You're trying to get the plates as close as possible without touching. You're touching the wax paper, but you got the 2 metal plates. You want to keep them electrically isolated from a conducting standpoint. You don't want them to be good conductors because then it'll short the capacitor out. So you can take 2 pieces of aluminum foil, put it in between a wax paper, and then roll them up. The hard thing is when you roll them up, making it where you can have a positive and a minus plate, or actually it's not positive and minus. In this case, it would be it would not be polarized. When we have a capacitor that has a positive and minus side, we call that polarized. But this one would be a non-polarized capacitor. So you could either plate could be positive or minus depending on what side you put the battery on. So what would happen is if you had this capacitor here, then you could actually take a battery and put across it. Take a battery, put across it, and then you could remove the battery and you could measure here with a voltmeter, and this charge would remain in place. So the charge would still be there. Now eventually it's going to slowly dissipate as electrons that fly through the air are going to neutralize any positive protons that you have. So eventually, and it's going to eventually escape, the electricity is going to escape out the edges because we said the distribution of charge is not uniform. It tends to go on sharp edges, and the sharp edges tend to want to pass through the air. So eventually it's going to discharge through those sharp edges, like we talked about. But it'll hold the charge for quite a while. But it does take time. There is a finite amount of time. Obviously, if you had a battery and you put it across a capacitor, if you looked at it, if you zoomed in on that, it's going to take a finite amount of time for that charge to go those plates. It's not just going to instantly happen. Nothing really happens instantaneously. Even light has a certain amount of speed that it has, so it's limited. Everything is limited.
Right.
So if we put a resistor in series with that capacitor, we can limit that charge rate even more, so that it could actually be significant. So we see here that we have a resistor in series with a capacitor, okay, and then we have a battery, and we can see that the charge time, the amount of time it takes to charge that capacitor up, has been increased compared to if you had no resistor at all. If you had no resistor at all, it would just charge up, almost instantaneously. Almost instantaneously. I said not instantaneously. But so this would be with no resistor, and then this would be with the added resistor. So you can also discharge a capacitor in a similar way, and the capacitor will slowly discharge the resistor. Okay. And then the amount of time it takes to discharge is dependent upon what we call the time constant, which is, we'll get into that a little bit more later. Actually, what we found is that if you multiply R times C, it gives you what we call a time constant. And the time constant is defined as being the amount of time that it takes to discharge to 0.63 of its final value, or 63%. So if you multiply the resistor times the capacitor value, then that'll be the time in seconds that it takes to discharge down to 63% of its final value. So represented on this curve, this would be the time constant. Okay, so we would say within 3 time constants, it's down to 95%. So 3 tau, it's down to 95%. And actually in 5 time constants, it's going to be down to 90, I believe it's 98%. Specifying capacitors. How do we specify them? The capacitance is specified in Farads, from Michael Faraday. A 1 farad capacitor connected to 1 volt will supply 6.28 times 10 to the 18 electrons. That's basically 1 coulomb. So that's the unit for charge. So we say that 1 coulomb is equal to, so we say charge is equal to C times V. So 1 coulomb of charge, that's the Q part, which is 6.28 times 10 to the 18 electrons. That's a lot of electrons, equals C, which would be a 1 farad capacitor, times V, which would be 1 volts, is equivalent to 1 coulomb of charge. So that's how it's defined. There's really no sense in asking why it's that way. It's that way just because someone said, hey, let's just make it that way. We have to make it some way. We have to define some amount of electrons, and we have to assign that to some amount of something that we can measure, which we're going to call voltage. And it's all arbitrarily assigned. So we would write 1 farad, but 1 farad capacitors are huge. There are some 1 farad capacitors that exist, but they're large. I mean, they're about the size. They would be large. They would be a couple inches in diameter and maybe several inches long, and they would be used for like a supplement to a battery or something like that. Normally we deal in microfarads or picofarads or nanofarads. Now, typically when you start to substitute capacitors, most capacitors are accurate within 20% of their marked value. Okay? So if a capacitor is marked 1 microfarad, that'll be plus or minus 20. Sometimes it's actually plus or minus 50%. So we're not super concerned with accuracy, but 50% is a whole lot different than 10 times difference. A 10x difference in electronics is huge, but many times a 50% tolerance is completely within reason. So don't be afraid if it says 10 microfarads on your lab to use a 15 microfarad or 20 microfarad. It's you have to adjust it. If you're going to do a time constant lab, just take note that if you use a bigger capacitor, the amount of time it's going to take to charge up is going to be proportionally different. So if you take a capacitor that's 2 times bigger than the one that's specified in the lab, then it's going to take twice as long to charge up. Okay, but it's not going to really destroy your ability to do that laboratory exercise. It's probably not going to destroy your ability to decouple your circuit or to provide a bulk decoupling capacitor in your electronic design. But now, with that said, you always want to make sure that you meet the voltage requirements of a capacitor. For example, the electrolytic capacitors over there are marked with a voltage. Now, some of them are 10 volts, most of them are 50. If you have a 10 volt capacitor and you put it on up to 20, yeah, it could zap that, or it could pop the top of it off. It looks like confetti. Those electrolytics look like confetti when you put a voltage across them that's higher than what the rating is for that capacitor. And you also notice that the electrolytic capacitors, and we'll have a lab on this, they're polarized, which means you cannot reverse the voltage across those. But ceramic capacitors and all other capacitors, you can. They're non-polarized. The only ones that are polarized are going to be electrolytics and tantalum capacitors. And we'll discuss that when we do a lab. Okay. So also remember too, when you're dealing with capacitors, many times if you look on a capacitor in an old TV or something and it says 200 volts on it, probably don't want to touch it. Because now normally we will choose twice the rating than what we need. So if let's say that we need 100 volts, we're going to put 100 volts across the capacitor. Usually we would get a 200 volt capacitor. So usually we have a safety factor of about 2 in that case. And if we had a 5 volt digital circuit, the minimum size capacitor we would use would be a 10 volt capacitor, not 5. Okay, that's our safety factor. Types of capacitors, they're often labeled according to their dielectric: ceramic, mica, polystyrene. Those are the fixed ones. We also have variable capacitors. Variable capacitors were used in the early days of radio, okay, to tune in the center frequency. And basically what that was is you had movable plates. So you would have a plate that would have a shape like a Pac-Man kind of, and you would have that close to another plate of similar design on a rotating shaft, and as you turn that, you could see that the surface area between those capacitors would change as you turn it. Actually, one of them really should be more like this, probably. Yeah. So that they have a different shape. Or you could come in here and you could have a shape like this on one side, and you could have perhaps a shape like this on the other, so that you get more of that variable capacitance effect. So you would turn it and they would start to overlap. And then you also have small trimmer variable capacitors as well. And yeah, do take note that electrolytic capacitors are going to be polarized. They have this indicator on them to show you where the minus terminal is at. like a ceramic capacitor will have a marking 0.1. Now the electrolytic capacitors normally are marked in microfarads. All other capacitors are always marked in picofarads. Okay, and there's a code for those. Usually the code will say like 223, and then usually there'll be a K. The K is the tolerance, and 223 means 2 with 3 zeros, and the answer is always in picofarads. So a 223 marking on a capacitor means 22,000 picofarads, which is the same as what? 22 nanofarads. Okay. What would a 224 be? Well, you're adding 1 zero, so it would be 220 nanofarads, 220 nanofarads. Clear? No? What would a 103 marking with a K? Normally there's a K or a J there. This is just the tolerance, so don't worry about that. It's like 20% or 50%. So 103 means 1 0 and 3 zeros. And the answer is always in picofarads. So 10,000 picofarads, which is the same as 10 nanofarads, which is also the same as 0.01 microfarads. Don't worry about it if you don't get it fully right now. We'll work on it during the lab time. But this is something that's commonly difficult for students, is capacitor codes. Okay, what are the symbols for a capacitor? Okay, so the symbol for a non-polarized capacitor looks like that. Okay, for a polarized capacitor, we will put an arc on the symbol to denote the minus terminal. And the non-arced terminal is going to be the positive side. And in order to denote variable, like a variable polarized capacitor, we would put a line through it like that. That means variable. That means that there's an adjustment knob where we can change and adjust the capacitance. Yes, there's a question? Yeah.
And the distance that our two symbols are away from one another, is that important? Just like what you showed me yesterday on the battery. You remember how you said?
Yeah, you don't want to draw a capacitor
away from each, kind of away.
Yeah, you wouldn't want to draw one like this, because that doesn't really look like a capacitor, right? You go like this and you go like that. The distance is too far. Okay. You're trying to indicate with the symbol. You're trying to indicate that you have two pieces of metal that are close together.
Absolutely.
So it doesn't really. It kind of defeats the purpose if you make them too far apart.
All right.
You want to make them as close apart as what you can.
Close together without touching.
Yeah.
Okay. Thanks.
Yeah. Because someone may infer something different if you go like this. It's like, well, what is that? I don't know. That's a wall with two poles sticking out of it. I don't know.
Sure.
Okay. We talked about capacitors being dangerous. This one's marked 600 volts, so I would not touch that capacitor. If you wanted to touch that capacitor, I would discharge it not with a wrench or a screwdriver, but through a resistor, because you're probably going to get a big spark. And that big spark could cause metal to fuse, that piece of metal could fall into your eye or something like that. How capacitors are used. Just wanted to mention really quick that, you know, it would be good to take notes on this. And I know I'm going to post, you guys probably know I'm going to post these on the website, but taking the notes is going to help you remember these things a lot better if you're actually writing and hearing it at the same time. So, how do you combine capacitors together? What happens when you combine them together? I guess that's the main question. What happens if you see a couple of capacitors in parallel? Well, as it turns out, the total capacitance in that situation is going to be the sum of the two capacitors when they're in parallel.
Right.
Okay? You're basically doubling, if you got two capacitors that are equal values, you're basically doubling the surface area of that metal. So the equation is going to be C total is going to be equal to C1 plus C2. However, if you have a couple of capacitors in series, you don't really get the same effect. Actually, if those are equal capacitors, you're actually going to get, the total effect is going to be half the capacitance. But if there's something other than equal, then you're going to have to use the equation C1 times C2 over C1 plus C2. But you can imagine, let's say we had each one of these capacitors is 1 picofarad. If we have 1 times 1, that's 1. And then divided by 1 plus 1, that's 2. So that gives you a half. Okay? This equation is the same equation that you have for resistors in parallel. So it's the opposite. That's the easy way to remember it. Don't remember two equations. Just remember the resistor equation. And just know that for resistors and capacitors, the equation is opposite. What I mean by opposite is, remember the other day we talked about resistors in parallel had an equation that looked almost identical to this equation, except that the C's were replaced with R's. Whereas the other day when we talked about resistors and we had series resistors, this equation was identical in the fact that they add, except, of course, the equation was R1 plus R2 is equal to R total.
So
Yeah.
if you had more than two, it would be the reciprocal of the sum of the reciprocal. Like,
Yeah.
C2.
Yeah, it
C2
is.
equals C1 plus C2. C2 equals C1 plus C2. Okay, C.
Yeah, which is this equation. This equation here is that if you have more than two, then you can use it's going to be the sum of the reciprocals and then take the reciprocal of that. Resistor and capacitor applications. It's just 1 over 1 over C plus 1 over C2, 1 over C3. And I will put these on Moodle. Okay, resistor and capacitor applications. What do we use resistors and capacitors for? They're the key ingredients for things such as a power supply filter. The capacitor will smooth the pulsating voltage and provide a steady DC current. So that's one application. We'll get more into those later. We're not going to talk about the details right now. Another application, a spike remover. Digital circuits, which we'll find out more about later. They can use a lot of current. They can draw that current. Those current spikes can cause glitches in the voltage. And so we use capacitors to eliminate those spikes. When we use the capacitor in this manner, we're going to call it a decoupling capacitor. Okay? Decoupling capacitor. And normally what that means is you may have this battery a distance away from your circuit board. Even if you don't have a distance away from your circuit board, typically you have capacitors across the power pins right next to the part. That's what we call decoupling. Decoupling. Eliminates the spikes, because those spikes can cause your circuit to glitch, and then you'll lose all your data and it won't really work right anymore. Yeah. Questions?
We used to use those a lot across a motor, starting up motor would be a spike go through system,
Yeah.
and if our power supply got weak or something, we would put a cap across there to take the spike at the source.
Using the capacitor that way, wouldn't that help get rid of some of the, I guess, the bouncing of the signal for like digital input, like the button, so
Yeah.
that would work the same way, so just, you wouldn't have like either unclear.
Yep. Basically, the reason we use capacitors, we can talk about it a little bit more, since you guys are interested in it. Basically, what happens is the battery has internal resistance. The internal resistance can be high considerably. I mean, 100 milliohms is considered high. I mean, for some circuits, if you have a large current spike, if you have 100 milliohms internal resistance and you have a 1 amp spike, I'm talking about just a spike. Now, many times when a gate switches, you may have a 1 amp spike just for a nanosecond or a microsecond. And during that time, that would give you what? A 0.1 volt drop. Okay, 0.1 volts, look at your TTL logic levels. There's a little bit of room you got there. If it's on the bottom or top, like if you're on the bottom, you only have 200 millivolts or something, maybe 300. So it can cause problems. And then when you add inductance of the wire that's actually delivering the current, inductance, now you've got electromagnetic induction. When you got a current change, what do you have? You have a magnetic field, and then you have an induced voltage. So added those together, okay, well, you've got a problem. So now the capacitor, what it does is, for changing signals, it has a very, very low internal impedance. In fact, the internal impedance is going to be equivalent to its ESR, equivalent series resistance. So that's why ceramic capacitors are used a lot for decoupling, is because they have a very low ESR. Yeah. And another way to think of it is like a water tower, or it's like a water heater, right? If you can have a tankless water heater, but you have no immediate supply if something happens. But a little capacitor right next to it is like you have an immediate supply of protons, positive charges. They're ready to go into your circuit if it needs it. Okay, if it needs it. Okay, we're going to have to move a little bit faster here. Okay, so RC circuit. You can also use a resistor and capacitor in series to get waveform generators. So we talked about the rise, the rise time and the fall time. It takes a certain amount of time to rise. If you put a square wave here on the input, this on the output, the signal is not going to instantly rise. It's going to be slow. And then when the signal falls, it's going to have a delay time as well. So actually what it winds up happening is that you can get like this sawtooth type waveform. Okay, so you can use it as a waveform generator. This waveform could be useful for making other things.
It's called an
Integrator. This is the integrator. It's configured as a low-pass filter. This is configured like a high-pass filter. And this is called a differentiator. These terms come from calculus, actually. Basically, what this means is the differentiator will allow fast moving signals to pass, whereas the integrator only allows slow moving signals to pass. And that's because a capacitor itself, that's what a capacitor does. Basically, it'll allow fast moving voltages to pass it, but slow moving voltages or DC voltages will not actually pass through a capacitor. So DC is about the slowest signal you can get, right? Slow signals will not pass through a capacitor. Fast rising signals tend to go right through a capacitor. They tend to go right through it. Okay? So what does that mean? So if I say a capacitor is configured in series here with this resistor, and we say that the fast moving signal will get through the capacitor, that means the spike gets through, but then when it goes to this DC level, for example, this is fast moving, this is the fast moving part, so it tends to get right through. But then the DC part of the signal, the capacitor tends to reject the slow moving or the DC part of the signal. So eventually it's going to decay down to 0. So now if we bring that signal low, now this fast moving part is going to tend to want to get through the capacitor. But then when you get to the DC part of the signal, it's going to want, again, to not let that signal to pass through. So that's why you wind up with this little spiky type signal. I don't really know what you call that signal. But that's the type of signal that you would get on an oscilloscope if you had a differentiator. This is also what we call a high-pass filter. It passes the high frequencies. What we mean by high frequency is a fast moving signal. A low frequency is a slow moving signal. So this is low freak, and this is high frequency. Okay, so that's why it's called a high pass. Well, it doesn't really say it here, but this is a high pass filter. We already talked about the 63% time constant. You multiply the R times the C and you get the time constant. So now we're going to move on to coils. Okay. What is a coil? An inductor, right? A coil is simply a coil of wire. It doesn't have to be copper wire, but many times it is. The copper electromagnetic speaker wire, that's copper wire that has been sprayed with like a polyurethane coating to make a clear insulator. And the reason they do that is because they don't want to use bulky plastic insulation, because that reduces the amount of turns that you can fit together. And we know with Faraday's law and with the electromagnet rules that we learned from the other textbook that we read, the elementary lessons in electricity textbook that we read, you want to have as many turns as possible to get that magnetic field. So, like we talked about before, electrons moving through a wire can cause an electromagnetic field or a magnetic field to encircle the wire. And passing a current through a wire that's been wrapped in a coil creates an even stronger field. The field is the principle behind the solenoids, motors, electromagnets, and many other things. And we know that a changing magnetic field induces a voltage, regardless of how that magnetic field is changed. So, taking a voltage and putting it across the coil will cause, because we know that during steady state, when a current is flowing through a wire, there's going to be a magnetic field. So we know that if we take a coil and we go from 0 volts to 5 volts instantaneously, like with a switch or a pulse or anything, then it's going to want to tend to create a magnetic field. But as that magnetic field starts to build up, we know that a changing magnetic field induces a voltage. So a voltage is going to be induced in that field that's going to tend to oppose the change that's causing it. Okay, what does that mean? Well, what that means is that if we take a voltage and a switch, we have a coil, and we have 5 volts here. Before we flip the switch, this coil is not going to have a magnetic field. It's not going to have any current. It's not going to have anything. Okay? But as soon as we flip this switch, current's going to start to flow through this coil. This coil has a very low resistance. It depends on the AWG wire table. How long is the wire? How thin is the wire? The diameter. So you look at the AWG wire table, but it's probably going to be maybe an ohm. It depends on how many turns you have. Could be up to 50 ohms for a very, very small coil. For a speaker coil, it would be like maybe 4 ohms. Regardless, Ohm's law says current's going to flow through this. If we, just to make it simple, if we say that we have maybe 5 ohm coil with 5 volts across it, the end value for the current is going to be 1 amp. That's going to be the end value. But the intermediate value is that the current's going to start to rush in. It's going to start to build up a magnetic field inside of it. Okay? The building up of the magnetic field is going to do what, according to Faraday's law? It's going to induce a voltage that tends to oppose, remember the Lenz's law apparatus? It's going to tend to counteract or oppose what's causing it. What type of voltage here would try to oppose the currents that's coming in? A plus up here or a minus up here? Yeah, the initial voltage across this inductor is going to be 5. That means initially, as soon as the switch is connected, there's going to be no current initially, if you look at it instant that it happens. Because instantly, it's going to try to start, a magnetic field is going to start trying to build up, but that voltage is going to be induced so as to completely oppose 5. If I have 5 volts here and 5 here, effectively, I have no current, but this 5 volts is slowly going to start to drop off. So 5 volts induced to 0. Okay? Which means that the total effect that's the total effect on the output. As soon as you hit the switch, it's going to tend to oppose that. The current is going to ramp up linearly. So if I go from 0 to 5, actually let me erase some of this. I've drawn too much. I needed my little eraser. There we go. Yeah. So if I go from 0 to 5 volts on the voltage, the current through the coil is going to look like this. Okay? It's going to go from 0 to 1 amp. Let's close that out. So the coil is going to tend to want to prevent, you can think of a coil as resisting a change in current. Okay? So a coil will resist the change in current through it, but it will not resist the change in voltage across it. That's why the coil immediately went to 5 volts as soon as it was switched, but the current did not go immediately from 0 to 1 amp. It took time to go to that value. Okay, so you can see a fast sine wave here. You can see a sine wave, a fast sine wave, and depending on the configuration of how you put the coil, if you put a battery in series with the coil with a sine, or a sine wave in series with the coil, the current through that coil is going to be large for a slow sine wave, but for a fast sine wave it's going to be small when we look at the current. Many times a coil will add ringing to a square wave. Okay, and the ringing comes because of the Faraday's law, which says a changing current will induce a voltage. And so that's a lot of the reasons why too we usually put decoupling capacitors across components, because there's normally inductance in the battery wire or the power planes on the board going to components, and we're trying to eliminate that ringing. Another comment is that inductors and capacitors tend to be opposites of each other. So a capacitor can cancel out the effect of an inductor, and vice versa. Now, if we take some of the energy, if we put a second coil, let's say that we have a coil, we have that magnetic field going through that coil. Let's assume that instead of putting a steady voltage across that coil, that we put a sine wave across that coil. Now we're going to have a magnetic field that's growing, that gets large and then it gets small. So it's going to get large. It's continuously going to be changing from large to small. So if we put another coil close to that magnetic field, so that actually those magnetic field lines cut those lines of magnetic force, then according to Faraday's law, we can induce a voltage in that second coil, and we can get a voltage out. And then we say that those two coils are electrically isolated from each other, but magnetically coupled to each other. Okay? So we can completely change a ground reference for a system. Some systems need to have different ground references, for example. Also, what this would do, for example, if you had one ground reference over here on this side, you could have a completely different ground reference on this side. So that's what we call electrical isolation. Another useful feature would be this signal now would be a differential signal, whereas this signal over here could have been a single-ended signal. Single-ended means one end is ground. A differential signal means you have no ground reference, typically. It's just two signals that are opposites of each other. So this signal on the right side could be used as for a DSL modem, a twisted pair type system, whereas a coax cable is used for a single-ended system. So this would be kind of an example of a bowline that's used to go from single-ended to differential. Another cool thing about this circuit is you can change the number of windings. You can have possibly 10 windings on what we call the primary side, and this is the secondary side. And you can have a 10 to 1, a 100 to 10. You can have 100 coils on the secondary side, and you can have 10 coils on the primary side. What we call that is we call it a 10 to 1 ratio, because there's 10 times more on the secondary side than there is on the primary. And what happens is you get a 10x increase in voltage. So that we would say that this sine wave on the secondary side, in this case, would be 10 times the amplitude as the one on the primary side. So we can use it for voltage amplification. We can also reverse that ratio, we could go from 10 to 1, and actually what we wind up with is a current amplification on the secondary side. So in this case, if we mark this as current instead of voltage, then we get a current amplification. Anytime you have a current amplification, you have a reduction in voltage, and vice versa. So it depends on what you want. If you're driving a speaker really is a current device. It takes current, it converts it to magnetic energy. So you're wanting to amplify current. So an audio transformer would have like a 10 to 1 or 5 to 1 ratio. You're going in the opposite direction. You're not trying to amplify voltage, you're trying to amplify current. Whereas if you're trying to send a DSL signal out to a customer, you're probably going to want to amplify voltage, because at the other end you're going to have a differential amplifier that's really detecting voltage, it's not detecting current at all. So it depends on what you're trying to achieve. So that's how we use transformers, and that's how they basically work. There's different types. They look, they have some that you can tune. Inside of old radios, you have antenna coils. In order to, like an AM radio coil, the antenna would be really long, so many times they just coil that up. Sometimes when an inductor is used when an inductor is used to prevent the flow of certain amounts of current, certain types of current, like high frequency current, high frequency voltage, when it's used to prevent the flow of that or impede the flow of a sine wave or a sine current, then we call it a choke. It's choking the ability of current or voltage to flow through a certain part of a circuit. And many times in RF we use those to prevent high frequency signals from going in on circuitry that we don't want high signals to be on. And of course the transformer we talked about. And one thing to note is when you take a coil and you have current flowing through it, and when you instantly remove that wire from that coil, it's going to want to, Faraday's law says the magnetic field is going to drop. It's going to induce a voltage to try to oppose the change. The change you're trying to make is going from a current to no current. It's going to want to continue that current, okay? Because it's trying to, Faraday's law says it's going to oppose the change that you're trying to make. It's going to try to undo what you're doing, so it's going to induce a very, very high voltage. It could, thousands of volts actually. And that's why you see the spark when you turn off your light, or you have a motor and you disconnect it. That spark is coming because of Faraday's law is inducing a voltage. It's trying to bridge that gap between the air. It'll actually make a voltage so high as to do whatever it can to give that spark, because it's not going to let you instantly change the current. It says, no, I don't think so. Even up to the point of overcoming the dielectric constant of air and actually bridging that gap. So Faraday's law is not going to let you get around what it says it's going to do. Now, transformers, a better transformer or a good construction of a transformer would be to have some type of magnetic material like steel or iron, and to make a circle out of it. The circle allows the magnetic flux to easily flow around it so that they're magnetically coupled. Okay, we call this flux. And you'll have a coil of wire on the primary side. You have a coil of wire on the secondary side. So that when you put a sine wave signal, the magnetic field, like we said, is going to be getting small and getting large. But actually the magnetic field is actually going to go, let's see here. Primarily, it's going to want to stay inside of this, because really what the magnetic flux tends to do is to, if you don't have this metal here, if you just had a solenoid, for example, it would tend to go like that. But if you provide another path for it, then it's going to tend to want to go in the path that's least resistance, easier for it to travel in. So it's going, ultimately what the magnetic field wants to do is to get from the north side of the magnet to the south side of the pole. Okay? So if you provided a better path here, then most of the flux will be contained in that path that you create for it. So that's basically the idea behind the transformer. You're forcing the magnetic path where you want it to go, and then you put your second winding where you want it to go. And then that's going to maximize its ability to magnetically couple the primary side to the secondary side. Normally what we do in the middle, it says laminated core, when we make that core, if we look at this side view of it, let's say this is our eye and we're going to look right this side view, then usually instead of making a core that's just solid, we usually laminate it with thin strips of metal, and what that does is it prevents currents, we call eddy currents, from flowing inside there. Those eddy currents would tend to heat up the core. And similar to the Lenz's law apparatus that we had, where we said that the current was flowing in that copper, and that will heat up and make the transformer more inefficient. So it's more efficient if it has a laminated core. So that's the purpose of that, to increase the efficiency. So it's time to go. It's actually past time by about 4 minutes, but if you guys don't have anything, if you need to go, then you can go. I'm just going to finish these slides.
Mr.
Yeah.
You're going to have them on Moodle also. So
Yeah, I'm going to have these on Moodle.
thank you, brother. Have a good weekend.
You too.
Get all of that.
So the turns ratio, in this case you can see this one looks like 1 to 1. So that means a 1 volt peak-to-peak sine wave on the input would give you a 1 volt peak-to-peak on the output. You can have a step up. That means if you have a sine wave here of 1 volt peak, then on the output, if you have a 5 to 1 turns ratio, and you have 1 volt here, then you would have 5 volts on the output. Whereas with the 1 to 1, you would have 1 volts and 1 volts. Now, with the step down, if you have a voltage and you have a 5 to 1 ratio, then if you have a 5 volts on the input, you're going to step down to 1 volts on the output. But a lot of times the step downs are actually used to step up current. So in other words, if we had we would use this step down to amplify some current. So if we had a 5 to 1, we had 1 amp here, then we could get 5 amps over here on this side. So it could pump up your current for going to a speaker. The different types, you have isolation. For example, on a, like I said, a balun for an antenna, where you're going from a single-ended to differential, or in a situation where you have two different grounds in a system. Many times in military applications, they want two systems to be completely electrically unisolated. That means you don't want the ground on one system to be the same as the ground on another, and so you have to use isolation transformers to do that. You have power conversion for telephone utility applications. One of the reasons AC electricity was used instead of DC. DC was Thomas Edison's electricity, and Westinghouse, and of course Tesla wanted AC electricity. And the reason the AC won out over the DC Edison system, even though Edison was first, Edison was the one that invented it, was because you have a lot of drop in the lines. And so if you pump up the voltage, your current, as you pump up the voltage, the current goes down, okay, if you have the same amount of power. So that current through the line represented the drop or the loss. So if you pump up the voltage, your current goes down, which means your losses go down, which means you can transmit the signal a longer distance. And so what we have thousands of volts on the main lines, but when it comes into our house, what will happen, I don't really know what the voltage here is, it's tens of thousands or something. But when we step it down, we usually have, it's a center tap, we have 240 across these, but if you use a center tap, then you can get 120, 120, or the 180 degrees out of phase. So you have 120 here, and you have 120 there. So for your dryer, you may use 240, but for your other applications, you may use 120. Yeah.
The line voltage outside here is probably 4 to 7,000. Is usually what it runs.
Okay, 47,000. Okay.
4 to 7,000.
Okay. Tesla coil, of course, named after Nikola Tesla. The guy invented the induction motor, had a lot of great inventions. You also have the automotive ignition coil. It basically takes a 5-volt battery, and by using this idea of many turns of wire and high ratio, turns ratio, it's a step-up transformer, then you basically have a few coils here, and then you have a lot of coils on this side. You may have 1,000 to 1 turns ratio or whatever, and you're getting a very large thousands of volts in order to spark across a spark plug. Okay, so the idea is you're actually breaking down the dielectric of air by creating a very high voltage. And again, like I said, audio is usually step down transformer. And then that's it for this section. We have the circuit symbols that we've talked about as an overview. You guys can look at it. I'll put them on Moodle. And then next week we're going to talk about the semiconductor devices. Any questions?
For the reason they want to jack the voltage up a long way, so they can put a much smaller wire to carry that current. So your hardware blocks. Put your phone over the